Okay, welcome to ilectureonline. In this next set of videos, we're going to talk about the stress and strain of materials. And we're going to start out with the very basic concept of what that really means. So first of all, we're going to define the term stress. Stress on a material is simply the force divided by the cross-sectional area over which it is applied. For example, if you have a beam like this and you push down on it with a certain amount of force and the beam has a certain amount of cross-sectional area, the stress is simply expressed in terms of the ratio of the force divided by the area. Now notice that if we have a larger cross-sectional area, like a much bigger beam like that, and we apply the same force, but the area is different, then the material will experience a different amount of stress. And you can see that if the area is larger, a larger area makes this a smaller quantity. That means there is less stress. So this beam is experiencing less stress than this beam, even though the amount of force applied to the beam is exactly the same. So you can see how stress is actually a function of both the force applied and the cross-sectional area of the material. So here we can see that there's a large amount of stress applied to this material, this beam right here, and here is a smaller amount of stress applied to the beam. The second part of the relationship between stress and strain is the second portion, namely strain. And the definition of strain is that it's a ratio of how much the material deforms, so let's call that deformation. In the case of a linear element here, like a linear beam, if we push down on the beam, we may make the beam a little shorter. We're deforming it by making it shorter, and that's called deformation. And if we find the amount by which it deforms divided by the original size of the object, so for example, this may be the deformation, the reduction in the length of the beam after we apply a certain amount of force on it. So let's assume we apply a force, and therefore because of the force applied, we actually make the beam shorter. So we deform the beam, and the ratio of the amount of the deformation divided by the original shape, which would be in this case the original length, is what we call the strain. In this case, if the deformation is large, we expect a large strain. In other cases, the beam may only, under maybe applying the same amount of force, may not experience the same amount of deformation. In this case, the deformation is relatively small, so therefore the ratio of the deformation divided by the original length is much smaller, and so therefore we can say that there's a small amount of strain on this beam and a large amount of strain on that beam. So why would that be? Why would some beams have a large strain when a certain amount of force is applied, and other beams will have a very small strain? Well, that has to do with the strength of the material of the beam. And so let's imagine, for example, that this is a beam made out of steel. And of course, if we take a look at the molecular level, if we zoom into a very small portion on the beam, and we take a look with a very powerful microscope, and we see that this beam is made up of atoms. And those atoms are usually, in a solid object of course, in a crystalline structure of some sort. They're usually locked into a certain structure. They do vibrate because of the thermal agitation, but they're all locked into one another. And the atoms are spaced just exactly right so that the forces between them is balanced out, and so they take up a certain amount of space between them, and they have a certain amount of space between each atom. So now what happens when you apply a force on a beam like that? Well, what you're trying to do is you're trying to push the molecules closer together. Now, if the molecules can easily be forced closer together, then you'll experience a large amount of strain. If the molecules experience a lot of force so that there's not a lot of room for them to be compressed together, then you experience a much smaller strain. For example, metals tend to be of the type where you have very, very small amount of deformation. You take a steel beam, you try to push on it, you're not going to make it much smaller. But if you take, for example, a beam made out of foam and you push down on it, you'll see that there's a lot of strain because the molecules do not, they're not very cohesive. There's not a lot of as much force between them to hold them in shape. So that's where you find a different amount of strain. Now what we tend to do with this, the concept of stress and strain, and by the way, one more thing I wanted to point out, notice that stress is force divided by area, and that would be newtons per square meter, and that is also those are also the units of pressure. So it turns out that stress is very synonymous with pressure, and so again, pressure is force per unit area. Large amount of force, small area, a lot of pressure. Small amount of force, large area, small amount of pressure. So there's a lot of similarity between pressure and stress. Now, if we find the ratio between stress and strain, so we take stress, which is force divided by area, and divide it by the strain, that ratio gives us an indication of what kind of material we're dealing with. For example, if we apply a small amount of, let's say we apply a large amount of stress, and there's a small amount of strain. In other words, just a little bit of deformation when we really push down on the material. If that ratio is large, what kind of material are we dealing with? We're dealing with a very strong material, a material that it does not deform very easily. And so this then would indicate a certain amount of property relative to the material, and we'll talk about what that is in just a moment. On the other hand, let's say we apply not a lot of stress, not a lot of force, and the strain is considerable, so that this fraction is large, so that fraction is small, because that's what it says right here. So again, small amount of stress, a considerable amount of strain, so the ratio is very small, and we're dealing with a very weak material, a material that very easily compresses. So here we're dealing with a weak material. Now, since this ratio of stress divided by the strain, again, stress is kind of like pressure, how much force we apply to it per unit area, and we divide that by the strain, how much deformation is relative to the original shape of the object. When we take that ratio, if that ratio is large, we're dealing with a strong material. If that ratio is small, we're dealing with a weak material. And so it turns out that we call this ratio something. We call that the Young's modulus. So the Young's modulus is an indication of how strong or how weak the material is. And strong or weak, we're talking about in terms of how much it can resist deformation under stress. And so, again, we're going to talk about Young's material in a future video, in a few videos down the road, a little bit more after we get the basics out of the way. But again, notice that that ratio does give us a property of the material, and so we'll talk a little bit more about that later. But here you have your basic concept of stress and strain and how that ratio actually means something to us, and we'll take use of that in future videos.